So if word problems always make you nervous, here is a step-by-step strategy that you can use to solve applied optimization problems. I technically went through this process without calling it that in the goat pen along the river problem that we just did in the last video. So the first thing is to draw a picture, take notes, define variables. So we had that pen along the river that I drew, and we called the height and the width H and W. Find a formula for what you want to maximize or minimize. We wanted to maximize area, so I found a formula for area. I'd said that area was equal to the height times the width. And then we had to get the formula down to one variable. That was where I used that constraint information to replace W with a formula involving H. Determine a reasonable interval A to B. This is usually the uncomfortable step for students, finding some sort of extreme value that makes sense on the ends. And then finding the absolute max and min on that interval. That should feel like a 4.3 homework problem after you've done steps 1 through 4. And then we answer the question. We need to have units on it. Remember that we're working an application problem. If you click on the second link in our Friday resources for the week, it will take you to this GeoGebra applet. And Tim Brzezinski has measured a can of cream of chicken soup. Not a big fan of cream of chicken soup, but we won't judge his soup choices. He measures the height of the can to be 4 inches and using a piece of paper measured the circumference to be 8.25 inches. Now, when you do this, you end up with a surface area, the metal that's used to make the can, you end up with a surface area of about 44 inches squared. And so the question we're going to ask is, given that they seem to want to use 44 square inches of metal, are they giving us the maximum amount of volume with that can? All right, so if you scroll down on this page, you'll see this. He's going to let you play around with the radius of the can. So what he's done is he's locked in the surface area of the can, the amount of metal used to make the can, at 43.8325. We're going to round that off to 44 in our calculations just to make it a little easier. And then he has the applet calculate the volume based on the radius that you choose. So you can see below the graph, you've got the R value. So you can enter in a radius of the can, or you can kind of pull that point. It's draggable along the graph. So I'm going to do that. Just kind of pull it around. And notice because the surface area is constrained to that 44 square inches, if you make the radius bigger, you have to make the can shorter because you only have 44 square inches of surface area to work with. All right, so there does seem to be a volume sweet spot somewhere in here where the radius is about 1.5 inches. Once you get past that, the can is getting really fat and short and doesn't have as much volume as when the radius was a bit smaller. So again, our goal is going to be to find the value for the radius that gives us the maximum volume given this surface area of 44 inches squared. All right, so I've reconstructed our can here. We've got the radius and the height labeled with R and H. Remember, that's our first step of an applied optimization problem, to draw a diagram and label some variables. Those are the two things that are changing as we're messing around with the dimensions of this can. All right, so what's our maximum volume using 44 square inches of metal? So I'm gonna have to give you two formulas here for the volume and surface area of a cylinder. So for a cylinder, the volume equals pi r squared times h. We're also going to need the surface area of this can. We're going to need to report the metal on the top, the metal on the bottom, and the metal around the sides. So the surface area formula for a cylinder is going to be 2 pi r squared plus 2 pi r h. Right, so the 2 pi r squared is the 2 pi r squared areas of the top and on the bottom. The 2 pi r h is the circumference of that circle, the 2 pi r, multiplied by the h, which gives you the surface area of the sides. Again, I'm not going to require you to know any formulas on the exam that we didn't use either in the videos, in Zoom, or on homework. So go ahead and add the volume and surface area of a cylinder to your list of formulas that you've been compiling since section 4.1. All right, so the next thing we need to do is to find our formula for the thing we're trying to maximize. So we want to maximize volume. So we want to maximize volume, which I've told you is pi r squared h. And we need to get that formula down to one variable so we can take its derivative and find its absolute maximum. So the way we get it down to one variable is to use our constraint. So our constraint is that 44 inches squared of metal. That's our surface area. So our constraint equation is that this 2 pi r squared plus 2 pi r h is equal to 44. So we need to solve this for one of those two variables. There are two r's in the equation and one of them squared. This is kind of like solving a quadratic equation for r. It's definitely going to be easier to solve for h. So I'm going to solve this equation for h. I'm going to subtract 2 pi r. squared from both sides. And that leaves me with 2 pi RH equals 44 minus 2 pi R squared. Now I'm going to divide both sides by 2 pi R. And there's a lot of simplification that looks like it could be done in that second term. So I'm going to divide these. I'm going to distribute this division, which is legal, over on the right. So I've lost the 2 pi R. This is now an equation for H. In the first term on the right, I can reduce the 2 and the 44. I can make this a 22. And the 2 pi R, so the 2 pi's will cancel, and the R will cancel out one of the R squareds on top. So we had a lot of simplification over there, which is nice. So I've got that the height is equal to 22 over pi R minus R. So that's not too bad of a formula there. And we're going to take that expression for H and we're going to plug it in for that H in our volume formula. And that will give us a formula for volume that only involves R. So I'm going to have my volume, let's call it V. I've got pi R squared. And for H, I'm going to plug in the expression we just found in green. So 22 over pi R minus R. All right, let's take this formula to a clean slide and find the absolute maximum of this function. All right, so here's our formula that we had at the bottom of the last slide, pi R squared times our expression for H. Let's go ahead and simplify this. We're going to distribute this pi R squared to both of these terms just to make it look better. I'm going to start calling this V of R now that we've got it down to one variable. So I've got 22 over pi R times pi R squared minus pi R squared times R. That's going to be pi R cubed. And we can simplify a little bit even more. These two pi's are going to cancel out. I've got an R down in the bottom that can cancel out one of the R squareds. And our formula looks better than ever. This is a volume formula that is 22R minus pi R cubed. All right, so we finally got our volume function figured out. We need to find the absolute maximum. So let's go ahead and find the critical points of this volume function. So we're going to find V prime of R. Let's see, 22R derivative will just be 22 minus the pi is a constant multiple. It's just going to go along for the ride. So we're going to take the derivative of the R cubed. So we'll bring down the 3 with the pi, R squared, and we're going to set this equal to 0. So let's add 3 pi R squared over to the right to make that a positive term. So plus 3 pi R squared. And I get that 22 is equal to 3 pi R squared. We're going to divide both sides by 3 pi. And I get that 22 over 3 pi is equal to R squared. We're going to take the square root now. And get a very weird looking critical value of 22 over 3 pi. Usually when I take the square root of both sides, I insist on that plus or minus being on the radical. Remember that we're solving for the radius of a can of chicken soup. So we're not going to put a negative radius on there. So I just chose the positive one. So let's see what the value of R is. I'm going to go to my calculator and take the square root of 22 divided by 3 pi. And I get 1.527. So R is equal to 1. Let's see, I'm going to round that off at 5.3. That's fine. So 1.53 inches. Remember that we saw that about 1.5 inches when we were playing around with that applet was the correct answer. So this makes me feel better about our calculations. We do need to prove that this is the maximum possible area, that we haven't accidentally found the minimum possible area. The interval I saved for the end on purpose. I wanted us to see what this critical value was first. So on the last one, I picked some sort of ridiculous values that didn't make any sense to sort of be our boundaries. I'm going to pick this interval over here. Our low bound again can be 0. So we can pick the ridiculous can that's going to have no radius. It's going to be all height, which obviously you can't put any soup in. So that would be our low bound. And for the high bound, you can look on the graph of the GeoGebra applet and see that the radius can't go much past 2. You start getting a negative volume calculation once you get past a little past 2. You're not always going to have a pre-programmed GeoGebra applet to help you figure out what this high bound should be. So we're just going to pick something that is beyond the 1.5 inches that we solved for. So I'm going to put 2 in here. just to make sure that we have some bounds on here, that we actually have found something that is the biggest possible volume and that we haven't accidentally found the smallest possible volume. All right, so let's find the volume at 0, the volume at our critical point, and the volume at 2. All right, so I'm going to go to my volume function. The most simplified version I had was here. I'm going to find volume of 0. Again, this is a stupid can. It's got a 0 volume. You're not going to fit any soup in that can. And then we're going to do the same thing for 1.53. And I'm also going to do the same thing for 2. All right, so let's let the calculator do the work for us. 22 times 1.53 minus pi times 1.53 squared. And I get 26.3. And let's see, the volume at 2, 22 times 2 minus pi times 2 cubed, which is 8. We got 18.9 or so. All right, so when we started off on this very long Campbell's soup can journey, we were looking for the maximum possible volume. So that volume is going to be this 26.3 down here. So our max volume is our 26.3. It's going to be 26.3. Volume is measured in units cubed, and we were measuring everything in inches. So this is inches cubed. And like the other problem, we'll mention that this happens when the radius is equal to our critical value, which was 1.53. And it turns out that this volume is not exactly the volume you get out of that Campbell's soup can that was measured in the pictures. They have a little bit less volume. So obviously they're taking something into consideration that isn't just surface area and volume.